That's another Dibs Physics video.
Hey there, physics people. We're back for another video as we now get into acceleration. We've already defined acceleration in our notes. You can go back to your notes and take a look at what it is, what the equation was, and all of that stuff. So just to review real quick, acceleration is a change in velocity that happens over time. Right? So what we're going to do today is we're going to look at a situation where an object accelerates, and then we're going to graph that motion, but not like the lab we did where we graphed a position versus a time. This time we're going to graph velocity versus time of the situation. So let's jump into our video that we're going to go through today. This is from a great movie called Back to the Future. You might have heard of it. Here we go.
Einstein! Hey, Einstein, where's the doc, boy? Huh? Doc!
Marty, you made it.
Yeah!
Welcome to my latest experiment. This is the big one, the one I've been waiting for all my life.
Well, it's a DeLorean, right?
Bear with
What
me,
did you
Marty.
do?
All your questions will be answered. Roll tape.
Okay,
and we'll proceed.
Doc, is that a Devo?
Never mind that now. Never mind that now. Not now. Not now.
All right, I'm ready.
Good evening. I'm Dr. Emmett Brown. I'm standing on the parking lot at Twin Pines Mall. It's Saturday morning, October 26, 1985, 1:18 a.m. And this is temporal experiment number 1. Come on, Heidi. Hey, boy, get in there. Now, boy. In you go. Sit down. Put your seatbelt on. That's it.
Whoa. Okay.
Please note that Einstein's clock is in precise synchronization.
Whoa. Okay.
Please note that Einstein's clock is in precise synchronization with my...
That's where I meant to pause it the first time. My bad, guys. If you take a look, does anybody see what's wrong with this video right now? That's right, it's backwards. Reason for that is, I believe, copyright stuff. I've been trying to find a good YouTube video of this for a long time. This is the only one that stayed up over a number of years, and I think it's because it's flipped backwards to avoid any copyright stuff. That's going to cause us some issues later on, which we're going to talk about. But let's roll the film, if you will.
with my control watch. Got it?
Right, check them.
Good. Have a good trip, Einstein. Watch ahead.
Got that thing hooked up to the car?
Watch this.
Yeah, okay. Got it.
Dummy, the car, the car! My calculations are correct. When this baby hits 88 miles per hour, you're gonna see some serious shit.
Excuse me. So notice the speedometer there. As we can see, the speed of the car is increasing. As time passes, this car is definitely accelerating.
Watch this, watch this.
Right up to 88 miles per hour.
What did I tell you? 88 miles per hour! The temporal displacement occurred exactly 1:20 a.m. in 0 seconds!
Ah, Jesus Christ. Jesus Christ, Doc, you disintegrated Einstein.
Calm down, Marty. I didn't disintegrate anything. The molecular structure of both Einstein and the car are completely intact.
Where the hell are they?
The appropriate question is, when the hell are they? You see, Einstein has just become the world's first time traveler.
So, an absolute classic of a movie. So here is kind of what I want to do with you guys. So let's take 1 second. Let's go to the whiteboard. All right. So what I want to kind of do here is use this as a situation of an object accelerating where we have a speedometer that's telling us our speed at certain points in time. So what we want to do is make this table, times in seconds, along with speeds in miles per hour, because that is the unit that we're using in this. I don't know what is going on with this thing. That is the unit we are using in this example. So we're obviously going to have our first point of 0 and 0. At 0 seconds, we are at 0 miles per hour. And we're defining that point because we're saying, hey, I'm going to start my stopwatch when the car has a speed of 0 miles per hour and starts increasing that speed. So now what I want you to do, I've actually gone through this setup here. Give me 1 second. So I've actually gone through the video and picked some moments in time where we can see the speed of the car. So let me grab those numbers for you real quick. So what I want you guys to do is to go and watch the video and record the time when the car's at 20 miles an hour, 34 miles an hour, 55 miles an hour, 63, 77, and 86. At all of these points in time, or at all of these speeds, we can read the speedometer and you guys will be able to stop and start your stopwatches. So you're gonna need a team of people to do this. What you're gonna do is you're all gonna start your stopwatch at 0, and then you're all gonna stop your stopwatch when the car gets to 20 miles per hour. Now, you might be thinking, how am I gonna do this, right? So you're gonna have your team of people. One person's gonna start their stopwatch at 0, stop it at 20. The other person's gonna start their stopwatch at 0, stop it at 34 miles an hour. Another person's gonna start their stopwatch at 0, stop at 55 miles an hour. And you're gonna record this data table, but there's an issue. All of the numbers on the screen were backwards. So I went to YouTube and I tried to find a version where all the numbers on the screen were forwards. But there was a little bit of an issue with that. So I found one version. However, it is titled not Back to the Future, but Fact to the Future, because it is indeed Back to the Future played in reverse. So we can watch this whole scene back, but this time backwards. It's quite entertaining. Yeah, what he said. So, as you can see right now, we've got a beautiful view of the speedometer. There it is at 88 miles an hour. And we can read that speedometer perfectly.
serious must you say? How are some years they have seen them? Stare, business, yeah,
Okay, so as you can see, it's a little weird, but this is going to let us do this easier. The problem is, since it's played in reverse, we have to do our experiment in reverse, which is going to be a little bit weird. So instead of everyone starting their stopwatches when the speed of the object is 0 and it starts accelerating, and then stopping their stopwatches when it gets to a certain speed, we're going to do it in reverse. So all of the members of your group are going to start their stopwatch at a certain speed, okay, and then stop their stopwatch once the car gets to a speed of 0. So we're just going to do the experiment in reverse, but we should be able to create this table. So what I want you guys to do is to get into groups of 3 or 4 people. Now obviously there's more than 3 or 4 data points, but you could play this video back a couple times. I'll have it linked in the description below. Okay, play this video back a couple times, work as a group, and I want you to create this data table. So again, groups of 3 or 4, your normal lab groups that you've been using are fine. Get in groups of 3 or 4, and I want you to make this graph in Google Sheets. I want you to do all the things we've talked about in terms of making a good graph, right? We should have time on the x-axis, okay? So our graph should look like this. We should have time in seconds down here, and then we should have speed in miles per hour on our y-axis, okay? And we should be plotting some points out here on this graph, wherever they end up being. So you guys are going to make this graph. We're going to see what it looks like. You're going to make a trend line. You're going to bring up the equation, and you're going to bring up the r² value as well, okay? So this is what I want you guys to do in class, is to work on this. And right now, pause this video, and then what I want you to do is we'll come back now in the next class period and talk about what we found, and then kind of get started with how to do things with these graphs. Okay. Hopefully you have done your graph and it is looking perfect. So before you move on, make sure your graph is done. But this is what your graph should look like. So we have a graph that should look something like this in Google Sheets. Now, there's a few points that I have on my graph. Otherwise, this is totally fictitious, but a few that are accurate. One is 0, 0. Everybody's graph should go through 0, 0 or be very close to it. Obviously, there's some error in our experimentation, but it should be close to that. And then another point is my last data point up here. For me, what I noticed was 88 miles per hour corresponded with roughly 37 seconds. So this means we should be able to find the slope of this line and do all the things that we normally did. Now, Google Sheets should have found the slope for you, but we're going to kind of calculate it the way that we've been doing, right? We're going to do our rise over our run. So let's do our slope equation over here. Slope equals delta y over delta x. So let's look at what our rise is. So as we go up, it looks like we're going from 0 to 88 miles per hour. So that is our rise. So I'm going to put in 88 miles per hour, and it is a positive value, over our delta x, which is roughly 37 seconds. So we go across 37 seconds. So what does that come out to be? Well, let's get our calculator going here. Let me see if we can't get it. Oh, there she is. All right, so I'm going to do 88 divided by 37. So hopefully having this kind of format out here helps you guys see what calculator inputs we're doing. So we end up with a slope of 2.38. Your slope might be a little different depending on your values, but it should be roughly within that range, okay? Now, let's take a look at the units here. We have miles per hour per second. So this is kind of a weirdly complicated unit. You can't even look at what I wrote. Let me get rid of the calculator. There it is. So we have miles per hour per second as the units of this. So what is this telling us? This is telling us the speed of this car increases by 2.38 miles per hour per second. So again, that's 2.38 miles per hour per second. Okay, so this is the acceleration of the car. We've got a value for it. But I'm going to ask another question now. How far did this car travel as it went from 0 to 88 miles per hour? Well, to do that, you guys would likely use some of the equations that we've talked about, right? Maybe you'd use this one, v equals distance over time, right? And maybe with that, you'd solve this for distance, right? So we'd have speed times time, and you'd be like, okay, I could just plug in the speed times the time. So could you come in here and plug in 88 miles per hour and 37 seconds? The answer to that is no, because of this. If you recall, that line over the V indicates average velocity, right? This car was not traveling at 88 miles per hour the whole time. So if I plug in 88 miles per hour in 37 seconds, when this equation does its thing, it's going to give us a distance that corresponds to a car going 88 miles per hour the whole time, which is not what happened. So we have to put in the average velocity. So let's go back to our graph. What would our average velocity be if we went from 0 to 88 at a perfect steady rate? You would be correct. It would be roughly 44 miles per hour. So this is going to be a little weird. If I go to plug this in, I go, okay, distance equals 44 miles every hour times 37 seconds. We have a little bit of a problem, don't we? The hours does not cancel with the seconds. So we can't figure out how far this car has gone. So what we got to do first is we've got to convert that 44 miles per hour, right, into meters per second. Let's get it to our lovely standard unit. So if you recall, the first thing we do is we go 44 over 1, and we set up our fraction, and we multiply by a blank fraction, and we got to do this piece by piece here. Actually, you know what? Hold on. I don't know what is going on here with this thing. We're going to give ourselves some more space. Can I delete these? Okay. So I'm going to give myself some more space here. I'm going to do it down here. All right. And let's do it in a different color. So we'll start with 44 miles in 1 hour. And you guys should do this conversion yourself. So I'm going to convert miles to feet first. Okay. And if you recall, 1 mile is 5,280 feet. Right? And now I can look and say, okay, miles is going to cancel out. I'll be left now with feet per hour, and we're just going to keep this going till we get to our standard unit. So feet, we're going to turn it into meters. If you're going, I forget all of these numbers, where is he getting these numbers from? All of these are on your reference table. So you can get all these values on your reference table. Now we've got it to meters per hour, which is wonderful. Now we've just got to convert hours to seconds. And if you recall this one's not on your reference table, but a lot of you remember that there are 3,600 seconds in 1 hour. And now hours cancels out, and now the only units we have left here are meters and seconds. So now we can go and throw this in our calculator and get a number here. So let me bring the calculator back up. All right, so I'm gonna do 44 times 5,280. I'm just gonna do this all in one shot here. Anything in the numerator, I'm gonna multiply. Anything in the denominator, I'm just gonna divide. So I'm gonna divide by 3.3. And then again, I'm gonna divide by 3,600. So I just go through this thing, do it like that. And there we go. We've got 19.6. This is now going to be meters per second, 19.6 meters per second. So 44 miles an hour is equivalent to 19.6 meters per second. So come back to our problem here. We're going to say, okay, distance is 19.6 meters per second times 37 seconds. So again, we're taking the average speed of this car. If it went from 0 to 88, in a steady rate, its average speed would be 44, right in the middle. So we're gonna take that 44 miles an hour, 19.6 meters per second, times 37, and we're gonna get an answer of 725 meters, and we'll just leave it right there, 725 meters. So this is kind of an interesting thing. We've got our acceleration of the car by finding the slope of this graph, okay? And now we did the distance by finding our average velocity. However, that was kind of awkward. There's to find the distance that an object travels. Not necessarily a car, but any object where we have a velocity time graph. So let's get rid of the calculator here and look at another way to do this. So here's my line, and that's my line specifically between 0 and 37 seconds, the time where this object was accelerating. And if I look at that, right, that occurs in this 37-second interval right here. That creates kind of a little bit of a shape, doesn't it? So this shape right here is what shape, guys? That's right, it's a triangle. Do you guys want to see something kind of crazy? Check this out, check this out, check this out. You ready? You ready? This is crazy, this is crazy. Okay, all right, here we go. So, just to recap, finding acceleration we can do by finding the slope of this line. But finding the distance traveled, or more specifically displacement, by finding our displacement, we can find the area of this shape. So we have a triangle here, guys. Does anybody remember the equation for the area of a triangle? It is 1/2 base times height. Now, check out how this works right now, because this is actually pretty nuts. So area equals 1/2. What is the base of this triangle? Well, the base of this triangle is down here 37 seconds. And I'm putting those units in there on purpose here. Another thing I'm gonna do, let me move my lovely camera. Oh, there we go. All right. And then what is the height of this triangle? Well, this height also has some dimensions to it, which is pretty weird. We have 88 miles per hour, which we need to convert. Oh, this is terrible. Let's convert this to meters per second real quick. Let's take our 88 miles per hour, convert it to meters per second. Just do a new page here. So we'll start with, again, 88 miles over 1 hour. And you're gonna do that same exact conversion. So I don't really know how to speed this up. So why don't we just go to our calculator and type in the same thing. You guys should do all of the work out, but we're gonna have 88 times 5280 divide by 3.3 divide by 3600. And you could also do this just by doubling the number that we had for the average speed. So we have 39.1 1 second. Here we go. All right, so we have 39.1 meters per second. Now, what happens here that's really interesting is if we look at the units, seconds is going to cancel out when we do this area calculation. And what is the unit that we're actually left with here? Meters. So this is really cool. We find the area, and you'll see that we get a very interesting number. We get area equals 1/2, so come back to our calculator here, 0.5 times 37 times 39.1. Oh my gosh, guys, we get 723 meters. Let's jump back to the work we did before. We had 725 meters. Now, why are they slightly different? This has to do with our unit conversion as we went from miles per hour to meters per second. It wasn't perfect. We estimated at 3.3 feet per meter there, and that's going to throw our values off by a little tiny bit. But still, if we find the area of this triangle on this graph, it will actually give us the displacement of the object, how far it's traveled. So this means from a velocity time graph, we can find the distance an object goes, we could find the speed of an object, and we could find the acceleration of an object, which means a velocity time graph can tell us everything we want to know about the motion of an object. So what I want you guys to do now is take a look at this next problem set. All right, so what we've got here is a velocity time graph on our homework that is posted on Google Classroom. So you guys should all have this. It's a little 2-page homework that you guys are going to be doing. And I'm just going to do some examples from it. I'm not going to answer any of the questions here. I'm just going to do some examples that will hopefully give you the tools that you need to do this. And those tools are kind of, what we've already talked about. So on a velocity graph, let's focus on a few things here. To get the velocity, all we've got to do is read the axis. And that's important. So to get the velocity of an object, all we've got to do is read the axis, right? And from this, right, we can answer the 3 main questions about the motion of an object. The amount, right, or the magnitude, the direction, right? Is it a positive or negative velocity? Now, we're not looking at slope this time. Be very careful with that, right? All we have to do is read the axis. And is it changing? Right? So just by reading the axis, we can kind of tell, what's going on with the object and what it's doing. So let's look at, an example of that real quick. So what is this object doing from point B to point C? So from right here to right here, what's the object doing? Well, in this case, our train is originally facing north, which means our positive direction is north, and our negative direction is south. So from B to C, this object has a velocity of 6 meters per second, and it's positive, so to the north. The entire time it has that velocity. So to answer our 3 main questions, we're traveling at 6 meters per second north, and it's not changing its velocity because that value is not changing. So now let's look at what's going on from maybe C to D. Okay, so from C to D, our velocity is changing. This car is slowing down from an initial speed of 6 meters per second to a speed of 0 meters per second. So we start out going 6 meters per second to the north, and then we slow down to a speed of 0 meters per second, right? And we can tell all of this just by reading what's going on here. on our y-axis because our y-axis is our velocity. Now, what if we're asked some other questions here? Okay, like, I don't know, let's say, hey, what's the displacement? So, what if we're asked about the displacement of an object? Well, we kind of learned that. If we find the area between the line and x-axis, that will give us the actual displacement of the object. As we saw in the Back to the Future thing, right? We found the area of that triangle, and weirdly, it gave us the displacement, or the distance that that object traveled. So let's look at our situation here of this object traveling from B to C. So here's my line at point B from B to C, and here's the x-axis from B to C. So what kind of shape gets made in this situation? That's right. It's not a square. Some of you said square, didn't you? You said square. You were going to say square, but it's actually not a square. It is a rectangle. And it's a rectangle because of the values on this axis. My y-axis is actually just 0 to 6, and my x-axis is going to be 10 to 40 seconds. So very, very different. So let's find the area of this thing real quick. Area of a rectangle is simply base times height. So I'm going to go and I'm going to do this base times height thing. So the base of this rectangle starts here. This is 10 seconds to here, which is 40 seconds. So the base is going to be 30 seconds. And the height of this rectangle is 6 meters per second. And what's cool, again, if we take a look at this, the seconds cancel out and we're left with just meters. And simply by doing this, we're ready to rock and roll. So let's get our calculator going here. Oh, got to turn it on. Stupid. So we'll do 30 times 6, and we're looking at 180 meters. So this thing travels 180 meters in that time from B to C, from 10 to 40 seconds. So we can use that to find our displacement. Now what we could also do is do this, right? Distance equals average velocity times time. And it ends up being the exact same calculation, doesn't it? Because my average velocity from B to C is 6 meters per second and the time is 30 seconds. So I'd end up doing the same math. But it gets tricky if we were asked to find the displacement of an object from C to D. Because from C to D, this object is accelerating, right? So from C to D, we end up with a shape that looks like this, right? Which is a triangle. So we'd have to find the area of that triangle to find our displacement. So it's important to make sure that when you find the area between a line and the x-axis, okay, that's going to give you the displacement for just that period of time. And it could be different shapes. Could be a triangle, could be a rectangle. Whatever it is, you can use that to figure out the displacement of the object. And then lastly, right, if we want to know the acceleration of an object, okay, so if we want to know our acceleration, we look at the slope of a velocity time graph, right? And I just want to put a note in here. Note, direction of acceleration is not the direction of motion. We spent a lot of time talking about this in class, if you guys recall. We talked about how the direction of acceleration is not the direction of motion. It's instead the direction that an object would be being pushed in order for it to change its speed. So if we come back to our graph here, I'm going to trust that you guys could find the slope of a line from C to D if that's what you're asked for, right? But from C to D, that's going to be a negative slope. Does that mean the object is going backwards? Does that mean it's going to the south in this case? No, it does not, my friends. From C to D, this train was traveling to the north. And I know that because the velocities over here are positive. Since I have from C to D positive velocities that entire time that I'm going from C to D, okay, because of those positive velocities, this car is going to the north. Now, the slope of this line is negative, which means our acceleration is negative. So that means our acceleration is directed to the south, which makes sense. If I'm going to the north and I'm slowing down, that means I'm being pushed backwards to the south in order to slow down. So use this as a lovely little, in a way, kind of cheat sheet for how to do this stuff with velocity graphs. I'm going to put up a bunch of different assignments, this little sheet with this graph and another being one, and another PDF from Mr. Shimberry that was really well put together, and he's got things phrased on there a little differently, might help you too. So you guys are going to be doing both of those in class this week, and all of this stuff is going to be due on Friday. So I'm going to be putting a post up with a bunch of stuff due on Friday, and you guys will put all of it together and submit all of your work there by Friday. So if you're absent, whatever it may be, you could get all this work done. If you're absent for, you know, like let's say you were absent for the making a graph thing in your group, you can get the data and do that on your own and submit that on Friday. So everything's going to be due on Friday this week. I know you guys got Halloween going on, so maybe you're doing some stuff outside of class time, whatever it may be. All of that is going to be due on Friday. Cool? Hopefully. And I just realized my microphone was on the table, so hopefully it was picking my voice up okay. That's brutal. It also is picking up my child, who is getting a little antsy right now. So I'm going to go, help him out, see if he's hungry, see how it goes. So have a great week, guys, and I'll see you later.